So writing chemical reactions, being able to identify reaction types, okay, things like that, are really, really important. And that's why I kept saying to you earlier, you need to make sure you can write formulas, write chemical names, because without that ability, you can't write chemical reactions. You won't be able to balance them. Basically, you're building a house without a foundation. It'll blow away or whatever. Okay. So we need to understand what the signs of a chemical change are. Now that's hopefully review. If a chemical change occurs, what are some signs we might see?
Change in odor.
Change in odor.
Bubbling or heat increase.
Okay. Bubbling or fizzing. Temperature change. Color change. Okay, I would say those are the big ones. Okay, and the second or the last thing would be a solubility change. That would mean maybe a precipitate gets formed because something formed in the reaction is no longer soluble. All right, so those would be the signs of a chemical change. In a chemical change, the change is not reversible. Okay, so as an example, a campfire is a chemical change. I cannot get unburned wood back after the fire. Okay? That reaction is not reversible. Now, it's not that all chemical changes are not reversible, but most are not reversible, and any ones that are require energy to be put back in. We actually use a reversible chemical reaction every day to power our phones. Okay? The lithium-ion battery in your phone, okay, is a reversible chemical reaction. There's a chemical reaction that occurs that releases electrons that power the device itself. And then when you plug it in at night, the electrons are forced to go the other way, recharging the battery. It's a reversible chemical reaction. Okay. Eventually, obviously, the battery dies. Okay. After a certain number of charging cycles, you have to replace it. Okay. But that's because basically all reactions eventually kind of quit. All right. Is everyone clear on that? Chemical reaction, signs of a reaction? All right, so we're going to go over the types of chemical reactions, how to identify them. It's very obvious how to identify them. They're all quite different. Okay, and learn to write them properly. Okay, so as we were saying, in a chemical reaction, the final products are chemically different than the starting reactants. Okay, so in a chemical reaction, this is what we have. Right? Let's say I've got a reaction that looks like this. Let's say I'm taking sodium hydroxide. I'm reacting it with hydrogen chloride. Okay? These are my reactants. Okay? That's not in your notes, so you might want to add that. Okay? So whatever I start with, whatever is going to react are the reactants. This reaction would produce these products. So what we have here is a very basic double replacement reaction. It still obeys Dalton's atomic theory, his rule about what happens in a reaction. In a reaction, atoms are separated, joined, or rearranged. In this case, they're rearranged. Okay? But I haven't made any new elements. I have made new compounds. My products are chemically different than my reactants. They contain the same elements, but they are not the same compounds. I started out with sodium hydroxide, which is a strong base, hydrogen chloride, which is a strong acid, and my products are salt and water. So I go from highly basic, highly acidic to neutral. Right? I have very different chemical and physical properties on the product side than I had on the reactant side. but I still have the same elements. Okay? So in that way, we're kind of obeying both things. A chemical reaction, the final products are chemically different, but we didn't make any new atoms. Okay? We just rearranged the atoms that we had. Does everyone kind of follow the logic of that? All right, the signs of a chemical change: color change, odor change. Okay, bubbling and fizzing often goes along with odor change. If you get an odor, what's been produced? A gas, yeah. So if you get bubbling and fizzing or an odor, that means that a gas has been produced by that chemical reaction. So when you were a kid and you mix like vinegar and baking soda together, right, and bubbles and fizzes and carries on, what you're getting is carbon dioxide gas being formed in that reaction. Okay, that's what's in the bubbles. All right, state change. So we could get a precipitate being formed from two solutions, okay, or an energy change, gets hotter or colder. All right, questions so far? So the first and most basic type of chemical reaction is a synthesis reaction. We call it a synthesis reaction because we are taking two materials and combining them to form a single material, or synthesizing a single material from building blocks. Okay? Typically, this is two elements reacting to form a compound. But it could also be a compound and an element forming a compound, as long as you get just a compound. For us, like 99% of the time, going to be two elements react to form a compound. Okay. So in this reaction here, I've got magnesium solid. That's what the S means. Okay, magnesium solid is reacting with oxygen gas to produce magnesium oxide. Now, you're not going to have to write in the states of matter, so you can kind of ignore the S's and the G's and the whatever. Okay, you don't have to worry about those in Science 10. You do in Chem 20, but you'll deal with it then. Okay, so this is magnesium reacting with oxygen to form magnesium oxide. Okay, now what are these big numbers for? Okay, I didn't expect anybody to know. It's more of a rhetorical question. The big numbers. The big numbers are there to balance the reaction. That is, to make sure that we obey the law of conservation of matter. That we don't create matter and we don't destroy it with a chemical reaction. That I have exactly the same amount of all types of atoms on both sides, the reactants and the products. Otherwise, like I say, I've created or destroyed matter, and I can't do that. So on this side of the reaction, in the reactants, I have two magnesium atoms, and over here, I still have two magnesium atoms. How many oxygen atoms do I have on this side? Two. It's a molecule of oxygen, but a molecule of oxygen is made up of two oxygen atoms. Okay, and how many do I have over here? Two. Remember, this two is kind of like this. It's saying multiply everything behind me by two. So there's two magnesium atoms, there's two oxygen atoms. That means I have the same amount of material on both sides of the chemical reaction. I haven't created any matter and I haven't destroyed it. So it's important to make sure an equation is balanced. Okay? We can see that a little better in the reaction down here. Right? So in this reaction, I have two atoms of potassium reacting with one molecule of bromine, which contains two atoms. Now, how do I tell the difference between, like I keep saying, this is two atoms of potassium, this is one molecule of bromine, and I said the same thing here. Okay? The difference is, if I have a big two, it means there's two of whatever there is behind me. When I write the two like this, it means these two things are bonded together. There's still two of them, but they're bonded together in a single unit. Okay? Everyone follow the difference there? All right, so we start out with two atoms of potassium, two atoms of bromine in a molecule, and we get two molecules of potassium bromide. Okay? So that means I still have the same amount on both sides. Okay? So in a synthesis reaction, two elements combine to form a compound. Questions on the synthesis reaction? Okay, so these are just things you'll have to memorize. Okay, there's not a lot of things to memorize in chemistry, but this is one of them. Okay, it's just memorizing the reaction types. The second simple one is the opposite, simple decomposition. If something is decomposing, it's breaking down into simpler parts. So a decomposition reaction is a compound breaking down into its elements. So what we see here is we have two molecules of water, and they just break down into hydrogen gas and oxygen gas. Okay? This is actually the process, essentially, by which rocket fuel is made. Okay? Getting water to split into hydrogen and oxygen is what Mark Watney was doing in The Martian when he nearly blew himself up. Okay? He was trying to electrolyze water with a catalyst, okay, and get the hydrogen and oxygen gas. What he didn't account for, he wanted oxygen gas, and what he didn't account for was all the hydrogen, and the fact that it blows up. You know, the Hindenburg, that big blimp that blew up, it's full of hydrogen gas. All right, so in a simple decomposition, we have molecules breaking up into their elements. Okay, so in this one, we have two molecules of nitrogen triiodide, and they're decomposing into nitrogen and iodine. Okay, now something that we're starting to see here is that some elements, when they're by themselves, form molecules, and some don't. Okay, if we go back to the last reaction, okay, when bromine is by itself, it's a molecule, but when potassium is by itself, it's individual atoms. Okay, and then when we look here, similar, right? We've got nitrogen forms molecules, iodine forms molecules, oxygen and hydrogen form molecules when they're by themselves. Right? These are what we call the molecular elements. They are the ones that are highlighted in color on your periodic table. Okay, so on your periodic table, you have some elements that are yellow. Okay, the yellow elements are molecular element pairs. That is, when they're by themselves, they form a pair with each other. So oxygen is O2, nitrogen is N2, okay? Chlorine is Cl2. Any of those ones that are in yellow, okay, form a pair when they're by themselves. Okay? And then the purple one, okay, is phosphorus. It forms a quartet or a tetrad. Okay? It comes in groups of 4 when it's by itself. Okay? So if a reaction ever says phosphorus reacts with this, it's saying phosphorus, P4. That's its elemental form. Okay? And similarly, you got one, I think it's in like salmon or orange or something like that, and it's sulfur. Sulfur forms an octet. It bonds with itself 8 times. So when sulfur is in its element form, it's an 8. And that is actually up at the top. If you look in the top right-hand corner of your periodic table, there's a little rectangular box that says polyatomic elements, I believe. Yeah. Okay, and it's got them listed there as well. Okay, I just color-coded them on your periodic table so that they're more visually represented. All right, those big numbers we were talking about again for balancing, making sure that we have the same number of and type of all the elements. Okay, let's check this reaction to make sure that it's balanced. How many nitrogen atoms do I have on the reactant side? 2. Okay, because there's no number beside the N, so there's just 2 N's. And over here there are 2 N's, so that's good. Okay, how many iodines are there here? How many over there? 6, right? 2 times 3 is 6, 3 times 2 is 6. Okay, so this reaction is balanced. Okay, everything is in equal amounts on both sides. Okay? And we're going to learn how to balance a reaction probably tomorrow or the day after. All right, questions on decomposition reactions? All right, so this is what we were just talking about, okay? These are your polyatomic elements: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine, sulfur, and phosphorus. I accidentally highlighted astatine and shouldn't have, okay? We just have to remember that those come as pairs or octets or tetrads when they're by themselves. All right, combustion reactions. Now, combustion reactions are probably the most involved ones that we'll look at. In a combustion reaction, you will have a hydrocarbon. That would be a molecular element containing carbon and hydrogen, hence hydrocarbon, right? Reacting with oxygen gas. In order for something to burn, there's got to be oxygen gas to support the combustion. All right, so anytime you see a reaction where you've got a hydrocarbon, some molecule containing carbon and hydrogen, plus oxygen, you're looking at a combustion reaction. Okay? The products of a combustion reaction, regardless of what the numbers are over here, are always carbon dioxide and water. Okay? In a complete ideal combustion reaction, the only products are carbon dioxide and water. Okay? So when your car is running, what's coming out of the exhaust pipe is carbon dioxide and water vapor. Okay? When it's really, really cold, and I don't know if you ever noticed this, but when it's really, really cold, water droplets come out of the tailpipe. Okay? Like you might see water like dripping out of the tailpipe on a really cold day. That's actually because it's so cold, the water vapor is condensing inside the exhaust system back into a liquid before it exits. And it's just being forced out, okay, by the force of the air. All right, so always you're going to get carbon dioxide gas. Okay? Obviously we know that carbon dioxide is something produced by the burning of fossil fuels. Burning of fossil fuels is a combustion reaction. Okay? And water vapor is the other thing that is produced. Okay? How many people camp in a trailer or a camper or something like that? Okay, do you do when it's really cold? Like you have to run the furnace? Sometimes. When you run the furnace, what do you notice on all the windows? They get frosty, yeah. And they get a lot of condensation on it. That's not from you, okay? It's not because you're breathing out. It's actually from the combustion of propane, which is what a furnace would burn, okay? It produces a lot of water vapor. And that water vapor gets into the air and it condenses on cold surfaces. Windows especially, if it's really cold, walls. Okay? You can actually get like water droplets forming on the walls, okay, if it's really, really cold. It's also why your car has to have a defroster in it. Okay? Your body naturally does the same process. When you burn sugar for energy in your cells, it releases water vapor. Okay? You exhale some of that water vapor, and it gets on the windows of a car when it's cold. You have a defroster to take it off, or they'll freeze up. They are fog. Making sense? All right. So in a combustion reaction, we have hydrocarbons. We have a hydrocarbon reacting with oxygen, producing carbon dioxide and water. Now, for combustion reactions, there's some special balancing rules, okay, that are different from all the other types. We're going to go over 5 reaction types, so the other 4 reactions will all be balanced the same way. Combustion reactions get balanced a little bit differently. All right, so I'm going to write down a couple of examples, and then we'll write down the balancing rules, and that'll probably take us to the end. Okay, so let's look at just this example here. It was actually the one we had up there. Okay, so this chemical reaction is the burning of propane. Propane is what your barbecue uses. So we have C3H8, that's propane, reacting with oxygen gas, producing carbon dioxide and water. Now, right now, this reaction is not balanced. Right? On this side of the reaction, there are how many carbons? 3. How many are there over here? 1. Okay, so this isn't balanced. If we're looking at hydrogen, same thing. There's 8 hydrogens over here. There's only 2 over here, right? And on this side, there's 2 oxygens, and over here there are 3. Okay, 2 of them here, and 1 more over there. So this reaction is nowhere close to balanced right now. So we need to balance it. So the first rule, and I'm actually going to write 2 reactions here, and then I'll write the rules underneath. Okay, so the first rule for balancing a combustion reaction is balance alphabetically, or in alphabetical order. Carbon, hydrogen, oxygen. Okay, so you balance carbon first, hydrogen second, oxygen last. Okay, that's the only rule we're going to need for the first one. Okay, so I want to balance my carbons first. How many carbons did we say are here? 3. But over here, I only have 1. So I need 3 times that many. So I'm going to write a 3 right here. This 3 now means instead of having 1 carbon dioxide molecule, now I have 3 carbon dioxide molecules. And that makes 3 carbons on both sides of the reaction. Okay, so now my carbons are balanced. My oxygens and hydrogens are still a mess. Okay, but I'll fix them next. Actually, I'll fix hydrogen next. How many hydrogens on the reactant side? 8. How many are over here? What times 2 will give me 8? 4. All right, so now I have 4 times 2 is 8 hydrogens and 8 hydrogens. So now both my carbons and my hydrogens are balanced. But my oxygens are not. Over here I have 2. How many do I have over here? 10. 3 times 2 is 6. Plus 4 more is 10. So this is actually a mathematical equation as well. That's why we have the plus. Okay, the arrow means equals. Okay, so the plus means add them together. So there's 3 times 2 is 6, plus 4 times 1 is 4. That equals 10. And I've got 10 oxygen atoms on this side. What times 2 will give me 10? 5. Now my reaction is balanced. I have 3 carbons on both sides. I have 8 hydrogens on both sides. I have 10 oxygens on both sides. All right, so that worked good for that one. That single rule, just balance it alphabetically. I'm going to need a second rule for this one, and here's why. If I do this same process, just balance it alphabetically, I'm going to run into a problem. How many carbons here? 4. Okay, so what needs to go here? Right. Okay, how many hydrogens are here? 10. Okay, what needs to go here? A 5. 5 times 2 is 10. All right, now if I look at my oxygens, 4 times 2 is 8, plus 5 more is 13. What times 2 will give me 13? Well, 6.5. Can I have 6.5 molecules? I can't. Okay, I can't write a decimal in here and say I have 6.5 of this thing, because we know we can't do that to atoms and molecules. It doesn't work that way. So that's no good. So we need a second rule, which I call the rule of 2. Okay? If there's an even number of carbons, start balancing with a 2. So if I start with a 2, This will get rid of my 0.5 problem because now I'm going to have twice as much of everything. Okay. So 2 times 4 is how many? 8. So I go over here and I put an 8 in front of that. 2 times 10 is how many? 20. All right, what do I need to put here to get 20? A 10. All right, now if I look at my oxygens, 8 times 2 is 16, plus 10 more is 26. What times 2 will give me 26? 13. Now I don't have a decimal. Now I have a whole number. Now I'm okay. All right, so that's an introduction to balancing. Okay? Those are the special rules for balancing combustion reactions. Balancing other types of reactions is much easier. There are no rules to remember except do it. Like basically start with the biggest number and balance. That's all you have to remember for every other reaction. It's just for combustion reactions, we got to have these special rules here. But don't pack up, we're not done. Hey, anybody need that anymore? Good? Okay. All right, the next reaction type is single replacement. Okay? Single replacement and double replacement, which are the 2 reaction types that are left, involve ionic compounds. Okay? In a single replacement reaction, it's an element reacting with an ionic compound. What happens, as the name would imply, is something gets replaced. Right? So basically, in a single replacement reaction, you have an element that's going to react with an ionic compound, and it's going to replace part of that ionic compound. And it's going to replace the part that it's like. So, copper is a metal. That means when it reacts with silver nitrate, it's going to replace the metal part of silver nitrate, which is? Which part of silver nitrate is the metal? Silver. Okay? So what's going to happen in this reaction is copper and silver are going to switch. Copper is going to end up with nitrate, replacing the silver, and silver is going to wind up by itself. What does this reaction produce? Pure silver. This chemical reaction can be used to plate silver. Right? Not in amounts that would be of any use to you, plus silver nitrate is really expensive because it contains silver. Okay? It's not like you could just get silver nitrate and throw a bunch of pennies in it and turn them all into silver and get rich. Okay? It wouldn't work that way. But the reaction works just like that. If I had a solution of silver nitrate and I tossed a bunch of pennies in it or copper wire, come back the next day, the solution that it's in will go from clear to blue, and a layer of silver will plate out on top of the wire or pennies. And so you have a bunch of pennies that look silver a few days later. And then the solution will turn blue because it would contain copper, all of whom's solutions and salts are blue. Okay, so it's an interesting reaction. All right, so in a single replacement reaction, we always have whatever the element is replacing the part of the ionic compound that it's like. So if this is a metal, it's going to swap out for the metal. If this is a non-metal, it'll swap out for the non-metal. Okay, so all you have to do in this reaction is just switch them. Okay, so we can see we get silver by itself, and we get copper with nitrate on this side. All right, is this reaction balanced? How many copper atoms are there here? 1. How many copper atoms over here? 1. Okay. How many silver atoms are there here? 2. How many over here? 2. Okay. How many nitrates are there here? 2. Remember, nitrate is NO3. This says there's 2 NO3s. Everybody okay with that? Okay. How many NO3s are there over here? 2. Okay, now I heard some people saying 6, and that's okay. There are 6 oxygens, right? This 3 only applies to the oxygen. So there'd be 6 oxygens and 2 nitrogens. 6 oxygens, 2 nitrogens. But we just take it as a whole. It's easier to do it as one piece. Okay? All right. That's what we're gonna be looking at tomorrow, spending a lot of time on reactions tomorrow. Okay. Reminder, guys, that your lab reports are due on Friday. Okay, make sure you're getting those done.